It seems like it's 1 o'clock, so we'll go ahead and get started. Welcome, everyone, and thanks for joining us. My name is Lauren Ballatin, and I work with the National Integrated Heat Health Information System based in NOAA's Climate Program Office. We're excited to have everyone here for the first session of the Heat Research webinar series. During this series, we'll be discussing a variety of research projects supported by NOAA's Climate Program Office, covering topics such as advances in heat projections and modeling, research on compounding and cascading impacts, resilience efforts in urban, rural, and coastal environments, local case studies, and more. The series will be showcasing the breadth of research taking place, as well as the impact of these projects on science and services across the country. In today's webinar, we are featuring projects supported by the Modeling, Analysis, Predictions, and Projections program, as well as the National Integrated Drought Information System. The presentations will discuss 3 research projects that have used advanced modeling and analysis to understand the drivers and outcomes of heat events. Do want to point out that registration is now open for the second webinar of the series, taking place on March 19th at 1 p.m. Eastern. And that webinar will focus on projects that have used advanced modeling, monitoring, and analysis to translate research on heat into real-world applications and tools. So if you're interested in joining that, please scan the QR code on the screen and you can register there. One quick announcement before we get started: we will have time for presentations after each speaker's presentation. So as you're listening, please do feel free to type your questions into the Q&A box so we can discuss them later. And if you're comfortable, please feel free to also add your name and your affiliation when submitting questions. So now I will pass it over to my colleague, David Benson, who will introduce our first speaker.
Thanks, Lauren. Hi, everyone. I'm David Benson, program staff with the Modeling, Analysis, Predictions, Projections program. And our first speaker for today is Dr. Ping Liu. He's a research associate professor at Stony Brook University's School of Marine and Atmospheric Sciences. His research focuses on the changes to planetary scale modes such as the MJO, ENSO, and NAO with global warming. He looks at dynamics responsible for those changes and their impacts on regional climate. Thanks for being here, Dr. Liu. Take it away.
Thank you, David, for the kind introduction. Today, I'll discuss our work on U.S. extreme heat, examine how regional temperature trends have shaped past changes, and how moisture amplification influences future projections. This work is in collaboration with Kevin Reed, Ming Zhao, Steve Garner, and Minghua Zhang. Observations show increasing frequency and duration of extreme heat globally and across the United States, with numerous record-breaking events in recent years. A primary driver is mean warming, which shifts the entire temperature distribution toward higher values. For example, the ERA5 below clearly shows this warming over the past 30 years. Beyond the mean shift, extreme heat is further amplified by moisture, persistent circulation patterns, and non-atmosphere feedbacks. Focusing now on U.S. extreme heat, 3 key questions motivate this study. First, how do regional temperature trends shape extreme heat statistics? Second, how should extreme heat be measured when moisture is included? And third, how will severity levels evolve under continued warming, given regionally varying temperatures and moisture changes? We used a 30-member SPEAR large ensemble developed in GFDL and evaluated against the ERA5 at matching resolution. focusing on summer temperatures like maximum and daily mean, as well as relative humidity. We began by examining the regional temperature trends across the United States. The spatial pattern here shows a well-known warming hole in May to August maximum temperature, with weaker or even negative trends in the central to northern United States, contrasted with strong warming in the west, south, and east. Importantly, this warming cycle has weakened in recent years, indicating that the warming hole is shrinking. The weakening of the warming hole becomes clearer when we examine the temporary evolution at the mean of the box we just showed. Earlier decades in the upper panel show more frequent negative anomalies in blue colors, while recent years are predominantly positive in reds. Using our bias-corrected projection framework, the seasonal mean warming hole is projected to disappear by late 2050s, although timing differs by month. Now, to examine moist extreme heat, we use the extended heat index formulation. This figure shows how moisture modifies apparent temperature or heat index. Relative humidity in the y-axis is sufficiently high. The heat index exceeds air temperature in red colors. In very humid conditions, the amplification could exceed 20 degrees Fahrenheit, for example, along this edge. However, in extremely dry conditions, such as this area, the regression formula can yield heat index values below air temperature, which reflects a known artifact. To maintain physical consistency, we constrain the heat index to be no lower than air temperature. A common way to define extreme heat is using percentile thresholds. However, the widely used 90th percentile shown in this map of heat index varies substantially by region. For example, in Canada in the north, the 90th percentile corresponds to values below 80 degrees Fahrenheit. It's not warm, at least. While along the Gulf Coast, it exceeds 103 degrees Fahrenheit, above the extreme caution category. For this reason, we use absolute heat index thresholds to define severity levels. Table here shows the NOAA's 4 heat index categories. These formulation are widely used for operational heat warnings. However, the highest category, extreme danger, with a threshold above 125 degrees Fahrenheit, is relatively rare in observations. So, to better represent the gradation of severity, we subdivide the upper 3 levels or 3 categories into 5 degrees Fahrenheit increments. This refinement more clearly captures both moisture amplification and escalating heat stress levels. Here's an example. During the 1995 Chicago heat wave, moisture amplification pushed the heat index near 120 degrees Fahrenheit. This corresponds to our highest severity level, but it's still below the extreme danger category. Before projecting the future moist heat, we first want to validate the SPEAR against the ERA5 for the historical simulations. The model reproduces the largest scale spatial patterns of summer temperature and relative humidity, first with very small ensemble spread in terms of climatology. For example, we show here, this is the third panel here, showing the daily spatial correlation coefficient over the Canos area. We see all above 0.95. But the mean, state, and trend differences are present here. We only show the mean biases in temperature, which is colder, and also relative humidity, which is larger or more humid. So to address this, we apply a bias correction framework. We replace the SPEAR daily climatology and the linear trends with those from the ERA5, and then extrapolate the ERA5 trend forward. But importantly, we retain the simulated anomalies from the SPEAR. This component is primarily represent the internal variability. This figure shows the projected increase in the number of days with a heat index above 80 degrees Fahrenheit. Are the changes during the next 30 years versus the previous 30 years. This increase ranges from roughly 10 additional days in most of the United States to as much as 2.5 months in the southwestern regions. So both the warming and moisture contribute to these changes. Beyond the total number of hot days, we also examined how severity levels evolve. This figure shows over the entire continent or United States, the average days for each level, starting with level 1, 2, 3, 4, and 5. So in the near term, like beyond several years, most of the increase occurs in levels 1 and 2. Higher severe categories begin to accelerate as level 3 and particularly level 4 over time. Starting in late 2040s, we see the level 5 gradually catch up. But since we show all the levels here on one graph, we barely see the actual average numbers as very large. This indicates not only we will see more heat, but that there will be a shift toward more dangerous heat, moist heat extremes. So, in summary, the U.S. extreme moist heat shows strong regional contrasts shaped by the historical warming hole and its rapid weakening. In the Western United States, warming primarily drives increases in extreme heat. In other regions such as Southern and Eastern, Western, the moisture amplification substantially increases severity levels. Looking forward, the higher heat severity categories accelerate by mid-century, indicating increasing risk of dangerous moist heat extremes. Our future work will further examine the underlying thermodynamic and the dynamical mechanisms. And thank you. I look forward to your questions.
Thanks for a very interesting talk, Dr. Liu. While we wait for some of the questions to come in, I had a few questions, a couple questions. You started talking about talking about this warming hole disappearing and how that plays a role in shaping the future of extreme moist heat. Can you just maybe explain a little further kind of what the warming hole is and the implications of this warming hole disappearing, kind of how that would lead to extreme more events in the future.
Okay, thank you. That's a very interesting question. If we go to this plot, the first one about the warming hole, this actually the warming hole in the past 4 years from 2021 to 2024, it was substantially weakened compared with like the end of 20th century, 1990s. But then we will see more small warming or even negative when being cooling in the central United States. So first, this is showing the rapid shrinking of the warming hole and also its weakening. Now, this in our study, we attributed this shrinking and weakening to mostly the trends. So that means the trend is becoming stronger. So the trends in the meantime shifts the mean temperature as we see previously as a major contribution to the extreme in statistics, like this one. So that connects the historical warming hole as overall regional differences over the United States, how it will impact the future extremes. In terms of the moist, now the moist, we know it's getting drier in the western and the southern. I didn't show that figure. It's getting drier. Also, that's also in the SPEAR model. So these two were, on the one hand, we have warming, on the other we have slightly drying. So the contribution to the heat index, which is nonlinear, but also give us the increase in different severity levels we have shown in the last slide. Does that answer your question?
It does. Thank you very much.
Okay.
I have a follow-up question, a second question. On slide 11, you showed kind of the 30-year increase or change from the current, future 30 years to preceding 30 years. And I was just curious if, I know you said the future work is to look at potential mechanisms and reasons for this. I was wondering if so far this has been mostly a dynamical, moisture transport into the region, or if like soil, or if you looked at soil moisture or land atmosphere impact, if you think they would have, if it would lead to some of the amplification that you're seeing, especially, that southwestern region that has huge changes over the next 30 years.
Yes, that's what we're looking at. Very important and very interesting. First, this is a 30-year difference starting from 2021 to 2050, because in comparison to the previous 30 years, starting from 1961 to 1990, I believe, or maybe I should say 1990 to 2020, 1991 to 2020. So these are the 30-year change. First, second, yes, we saw the drying first in the south. We see the drying in the west. But I'm sorry, I did not show that. We see that in the model, also in the observations. Now, our preliminary analysis did show the large-scale transport, as just indicated, contribute largely to this change in moisture. So, but whether this also related to the land, atmosphere feedback or interactions, we don't have a specific answer to that yet in this specific change, but we hope we'll get some more information from the model.
Thanks, Dr. Liu. We have one question from the audience talking about this particular chart, saying, does the area above the polygon mean there's no increase in days projected, or does that simply mean that we don't model that region? So I guess the northern part of this chart here.
That's very interesting. In terms of that polygon itself, I will analyze how it will change in the future. For this specific webinar, I prepared the entire United States to show an approximate regional difference, but that definitely will be on my mind. Thank you very much.
All right, thanks very much, Dr. Liu. I think we'll move on to our next speaker. Our next speaker for today's webinar is Dr. Jane Baldwin. And Dr. Jane Baldwin is currently an assistant professor in the Earth System Science Department at the University of California, Irvine. She previously was a Lamont Doherty Earth Observatory postdoc at Columbia University and did her PhD work in atmospheric and oceanic science at Princeton University in conjunction with NOAA's GFDL, Geophysical Fluid Dynamics Lab. Excited for your talk. Thanks for being here. Whenever you're ready, please take it away.
Okay, great. Can you see that? Hello?
Not yet.
Okay. Oh, let me share my screen. I'm sorry for the delay. I'm sorry. Okay. I don't know where the presenter. Oh, here we go. I apologize. Can you see that?
Yes.
Okay, great. Sorry for the delay. So, hi, my name's Jane Baldwin. As David said, I'm an assistant professor of Earth System Science at University of California, Irvine. Really delighted to be here today. I owe a lot to NOAA. My PhD, as he said, was at NOAA's Geophysical Fluid Dynamics Lab in large part. And I'm today going to present some work that's funded in large part by a grant through NOAA's MAPP program. So, for this project, we've been seeking to understand tropical cyclone extreme heat hazards using global climate models. The work I'm going to present today, a lot of the analysis has been done by my student, Samantha Frucht, who's fantastic. I encourage you to reach out to her in addition to me if you have any follow-up questions. So first I want to define what a tropical cyclone heat compound event is. So here we're thinking about a situation where a tropical cyclone, such as a hurricane in the North Atlantic or typhoon in the West Pacific, makes landfall. When these events make landfall with significant intensity, this leads to damages and frequently power outages, which can last for some time, which make it challenging to use typical methods of cooling, such as air conditioning and fans. Now, the concern here is if this event coincides or is shortly followed by extreme heat, which is already a deadly weather event in many cases in the US, this could lead to significantly amplified impacts from the extreme heat. So you have a setup for a potentially very impactful and dangerous compound hazard. And we have seen various events that have exhibited some of these dynamics, such as Hurricane Maria in Puerto Rico, which led to long power outages and exhibited amplified heat-related mortality. So the question is, can we try to construct some understanding of the probability of having these events across the entire globe and how these events might evolve with climate change? Now, the first study that tried to quantify the hazard of TC heat events across the globe was actually not terribly long ago. It was Matthews et al. 2019. So this is a relatively new type of compound event to study. And what they did was basically look at where the point of landfall of various historical TC tracks coincided with extremely high heat index values. And based on this relatively stringent definition, they concluded that in the historical record, the only place that met this definition was actually a few TC heat events that occurred in Northwest Australia. However, they did this exercise where they essentially took those historical temperatures and added a delta corresponding to about 4 degrees of warming to them and kind of reanalyzed the probability of having TC heat compound events, demonstrated that if the historical events had occurred in this kind of pseudo-warmed future, you'd have many more events, and so concluded that we'd likely see a growing frequency of these relatively rare TC heat compound events with climate change. Now, I think this was a great study for sort of getting the conversation going about these events. However, a significant limitation of it is it didn't consider the fact that tropical cyclones are also expected to change in various ways with global warming. And so the goal of our present work is to try to assess the future TC heat compound event hazards across the globe using high-resolution global climate models, or GCMs, which can explicitly simulate tropical cyclones and their potential changes with climate change, so we can, in a self-consistent way, see how the frequency of these TC heat events might evolve, accounting for the fact that the TCs might be changing as well. So the main tool we're going to be using overlaps with Ping's talk. So we're going to be leveraging the SPEAR large ensemble. SPEAR is a GCM developed at NOAA's Geophysical Fluid Dynamics Lab that simulates the atmosphere and land at about a 50-kilometer resolution, though it's a fully atmosphere-ocean coupled model. So there's a dynamical atmosphere and a dynamical ocean. It simulates TCs up to about category 3 in strength. And this is typical for GCMs at this resolution, so they do have some bias in terms of the full intensity distribution of TCs they simulate. And we explore 30 ensemble members of this model, simulating the historical record through end of this century. Here's an example of what the TC tracks look like in SPEAR, and essentially it does a good job in capturing the typical trajectories of tracks and sort of basin to basin differences in tracks. But again, there is that bias in TC intensity, and so I won't go into this in detail in this presentation, but actually our first significant effort in this project was thinking about how to intelligently bias correct both the TC intensities and some aspects of the heat data so we could confidently apply thresholds that are actually relevant for impacts. So in thinking about any extreme event, if you're looking at quantifying its frequency, you first have to figure out how you're going to define that event. In the case of TC heat compound events, because it's a relatively new event to study, there is no one set definition. So how we've chosen to define these events is we look for landfalling TCs with winds greater than about 50 knots. This is a intensity at which damages from TCs start to pick up significantly. And then we look at cases where this coincides with heat index values greater than about 100 degrees Fahrenheit falling within about 1 week of the TC. Now, again, because there's no one set definition, we test the sensitivity of our results to all these different particular aspects of the definition, how hot we require it to be, the duration following the event, how strong the winds need to be. But for the results I'm going to show here, this is the definition we're using. To make this a little more explicit, let's say you have a tropical cyclone tracking from the ocean onto the Australian continent. Now, we are just going to focus on points where the TC is over land, because again, we are focused on projections that are relevant for human impacts. So we care about TC heat events occurring over land for this work. Now, if you hone in on one of these TC points, what we're essentially doing is looking at an approximately 2-degree radius around each 6-hourly TC point and asking the question, within the 7 days of landfall, how many times do we see this 100 degrees Fahrenheit heat index be exceeded? And for basically each location that experiences at least one instance of this extremely high heat index value, we count that as a TC heat event occurring. Now, to justify that we think SPEAR is doing a reasonable job in simulating these events, I want to first compare our historical record of TC heat compound events to what we find in SPEAR over the historical record, which we define here as 1980 to 2019. So first in the top panel, we're looking at when we combine atmospheric reanalysis with IB tracks, which is basically historical tropical cyclone tracks. And you can see a variety of hotspots of tropical cyclone heat events emerge, such as in the around the Gulf of Mexico, along the coast of East Asia, Northwest Australia, and parts of Southeast Africa. One thing to note is this is a significantly broader distribution than was ascertained in the Matthews et al. Study. And that has to do with some aspects of their definition that were particularly stringent regarding the threshold of heat and assumptions about requisite wind speeds. So, I think, again, one can argue about what exactly is the appropriate definition, but I think there's reason to be concerned about TC heat events in potentially all of these places shown in the map above. Now, what I'm showing below now is the distribution of TC heat events we find in SPEAR. And so we're able to reasonably simulate the spatial distribution of these events and to some degree the frequency of these events as well, which is reassuring and gives us confidence in moving forward in the future projection using this model. Now I want to hone in for a second on a few hotspots of hazard that I mentioned. And what I'm plotting here is the temporal spatial average of the average number of TC heat events per year in each of these regions in the observed record, which is shown in gray. Now, in red is what we find in SPEAR. So in general, you can see that there's some significant correspondence between places that have relatively higher or lower hazard in SPEAR versus reanalysis. That said, if we thought SPEAR was doing a perfect job simulating these events, we'd expect the gray bar to fall within that black error bar and the red bar. Now, that black bar is representing the spread we see across the SPEAR large ensemble. So it's basically a representation of uncertainty due to internal variability. And we find that in some regions, the observations do fall within that black bar, indicating SPEAR is arguably not very biased in simulating TC heat events in that region. However, for a number of regions, such as East Asia and Australia, SPEAR is probably somewhat underestimating the frequency of these events. Okay, so now what do we see in the future projections of these events? So first, I'm going to look at just the global sum of the total number of TC heat events per year. First, if we look at the historical record, we see, as expected, that TC heat events have gradually increased, which makes sense with comparison to the Matthews study in terms of the fact that we know that extreme heat has been increasing over this period. Now, the question is, how do these trends... sorry. Now, the question is, how do these trends change in the future? Our expectation, again, based on prior work and the fact that many studies have shown that extreme heat and compound extremes related to extreme heat are increasing in the future, is that the frequency of TC heat events will continue to increase. And just for reference, the solid line is the ensemble mean, and then what we see shaded is the ensemble spread. However, what we find in the SPEAR large ensembles, quite surprisingly, is that when we move from 2020 to end of century, the number of TC heat events stays about the same, or if anything, decreases a slight amount. So the question is, why is this happening? And in thinking about a compound event like this, the first place to look is, well, this results from a combination of trends in heat and trends in TCs. So which of these changes is the culprit here? If we look at changes in extreme heat over this period in the SPEAR large ensemble, the number of global mean heat index exceedances for the threshold we're using is clearly increasing over time, as we'd expect. So this doesn't seem to explain the slight decreasing trend we see from 2020 on. However, the number of tropical cyclones in the SPEAR large ensemble is actually decreasing over time. And this is consistent with another study we've collaborated on with folks at Columbia that have looked in some detail at the fact that SPEAR is showing a decreasing number of TCs. Now, I should mention that this is not necessarily surprising in the sense that other high-res global climate models have simulated decreases in tropical cyclones over time with global warming. And in fact, there's quite a bit of debate in the literature about whether tropical cyclone frequency will increase or decrease with warming. So as a result, I wouldn't view what we see in the SPEAR large ensemble as what definitely will happen. However, I think it represents a plausible reality that could occur. The fact that TC frequency may decrease is well within the range of our current scientific uncertainty, and it suggests that it's really important to consider what's the potential changes in TCs in looking at this compound extreme. Now, to close, I want to briefly show a little bit about what we see in terms of spatial and regional trends moving from now into the end of century at different warming levels. So again, here are those hotspot regions where we're looking at the number of TC heat events per year. And what's shown below is the change in the number of TC heat events at 2 degrees warming compared to the historical period 4 degrees warming. And so we see some somewhat consistent spatial trends emerge in the sense that, say, Japan is seeing a large increase in TC heat events, whereas Florida is seeing, and the Caribbean see a bit more of a decrease that gets exacerbated as it gets warmer and warmer. And so this suggests that even though in the global mean we might see a slight decrease, there's a lot of spatial variability in these trends. And on top of that, if you average over each of these regions and look at different warming levels, you see some kind of consistent patterns across warming levels. For example, East Asia and Japan consistently show increases in TC heat events. For the most part, we see decreases in the Caribbean, especially at higher warming levels. However, if you add on those black bars representing the spread across ensemble members, we see that internal variability matters a lot. The only place that actually confidently is going to see an increase in these TC heat events or any particular sign of change is Japan. Whereas a lot of these other regions, what will happen in the real world will depend a lot on how we roll the dice of internal variability. So to wrap this up, SPEAR suggests TC heat events may decrease in the future. Changes in TCs should be accounted for in future studies of these compound extremes because it can significantly affect the trends that you see, whether they're positive or negative. There's large uncertainty regarding regional trends due to internal variability, which speaks to why it's very important to analyze these types of extremes using something like a large ensemble. And future work, this is our preliminary results that my student is still working on. We're going to test more about the sensitivity to different definitions of TC heat events, more rigorously quantified the relative contribution of TCs and heat to future changes in these results, and we're analyzing a few other high-resolution VCMs. So thanks so much. I'm happy to take questions.
Thanks so much, Dr. Baldwin, for a very interesting talk. We probably have time for one question, and this is a question in the chat. It says, how much of the observed compound TC heat events are also a product of pre-existing conditions, such as drought or ongoing heat waves?
That's a great question. I certainly don't. I think, unfortunately, the answer is I don't know. That's not something we've analyzed specifically yet. I think that would be interesting to look at to see. I mean, one thing we could potentially do is look at whether TC heat events are ones that where typically the heat started before the TC. One thing I will say, I didn't present I have a postdoc who's looking at the physical intersection between TC in a bit more detail. And an interesting result that she's found is that most TC heat events that have occurred in the historical record exhibited extreme heat both before the TC and after the TC. So I think that speaks to the fact that there's a good chance that when TC heat events occur, a fair amount of the time, the heat wave had already started before the TC. And part of the physical justification for that is when TCs make landfall, to first order, they tend to, at least at first decrease temperature because they come with significant cloudiness and rainfall that moistens the surface and increases latent heat fluxes from the surface. So I guess that actually a fair amount of these events have the extreme heat starting before the TC. And the drought's an interesting question.
Yeah. Thank you. One more question. I think we can have time for one more. It says, is there a good explanation as to why the SPEAR model projects an overall decrease in TCs?
To dig into that in gory detail, I encourage you to look at which should be coming out in the next few months, the paper by Wenchao Chu from Columbia's group. I think maybe the general answer is that the increasing amounts of work demonstrate that changes in the frequency of TCs result from a change in how whether the environmental conditions are good for TC intensification, but also there's been some increasing discussion about this idea that pre-TC seeds, so like kind of small vortices that are important for the beginning of TCs changes in those may have some impact on the increase or decrease in frequency, but that's a very active area of debate. So I encourage you, if you want to get into it in detail, I encourage you to look at that paper. I'm happy to discuss it more offline.
Thanks again, Dr. Baldwin. Our final speaker for today is Dr. Lori Huning. Dr. Huning is an associate professor at California State University, Long Beach in the Department of Civil Engineering and Construction Engineering Management. Her research broadly examines topics in the areas of hydrology, water resources, climate, and extreme events. Her research aims to better characterize hydrologic processes as they evolve with a dynamic atmosphere and impact natural and human systems. Dr. Lori, thanks for being here. Whenever you're ready, please proceed.
All right. Thank you for the very nice introduction, and hopefully you're able to see my slides in full screen mode here. As mentioned, I am Lori Huning, and today I'll be talking about a few projects related to warming in snowy regions that my team and I have been working on. Here I've listed the co-PIs of my current NOAA project, which will be one of the main focuses of this presentation. Before getting started, I'd also like to acknowledge the large and incredibly great team of collaborators who have contributed to some of the work that I'll be sharing today. So just to kind of shift gears from the previous presentations, we're going to be talking a lot about snow. As you're probably aware, snow is critically important across the globe. In fact, snowmelt provides over 1 billion people around the world with water. Snow affects climate and biogeochemical processes in a wide variety of sectors. And so as temperatures rise, we must really better understand these impacts of warming on the snowpack, whether we're talking about warming across an entire season or even a short event like a heat wave. So we're gonna, start looking at the implications of warming. First, by looking at warming across the winter season, we're going to focus on its impact in terms of the snowpack in the Sierra Nevada, and then we're going to transition into heat waves across the Western U.S. that drive snow losses. As many studies have indicated, extreme events are anticipated to become more severe, persistent, and even more frequent throughout many parts of the world, which will alter fluxes in mountainous regions and enhance interactions between various extremes, such as droughts and heat waves. So, together, warming and extreme temperature affects the fate of snow, so the amount of snow water equivalent, or SWE, in a region, when and where the snowpack will melt, and at what rate, which in turn impacts the water supply and the people and plants and animals that all depend on it. So to understand the impact of warming on the Sierra Nevada snowpack, we looked to the historical record using a snow reanalysis, and we asked the question, what are the effects of 1 to 2 degrees Celsius of warming on the SWE volume stored across the mountain range? And so what we did was we sampled the SWE distribution, given different temperature levels, and that's what you see here in the top figure on the left. And so it's not surprising that you see a SWE shift, a distribution in a shift in the SWE distribution to the left for higher winter temperatures. But what we really wanted to understand was, and we computed the probability of SWE exceeding its long-term average value conditioned on temperature. And those results are what's summarized in the figure here on the lower left, and also the infographic on the right. And so to summarize, we showed that for a 1 to 2 degree increase in the winter temperature, it becomes about 20 to 40% more likely to have below average SWE. So in other words, you can think about it that the region is becoming more prone to drought conditions with a few degrees of warming. And oftentimes we've seen historically that large wildfires across the Western U.S. are also associated with such conditions. Not only does warming pose challenges for water resources management, but when less SWE accumulates, it also provides spring and summer runoff, but that center of mass of the snowpack tends to shift to higher elevations, which then alters things like flooding potential and the effectiveness of our current in situ network. And so in recent years, we've also seen wildfires moving to higher elevations across the Western U.S. as well. So layered on top of kind of this overall warming that is expected to occur, observations and studies also suggest that more heat waves will be experienced across these regions, mountainous regions, and in the presence of snow. So we're going to transition now to discussing heat waves. And when people think about heat waves, the first thing that comes to mind is those kind of midsummer sweltering temperatures. But what we're looking at in our project is, what is a winter or spring heat wave and in the presence of snow. So we're interested in heat waves that result in measurable snow losses, and we want to understand associated drivers and conditions that cause those losses. We're also characterizing impacts of heat waves on stream flow and its components and looking at links to drivers of SWE variability and change, really to inform water resources management and our stakeholders. So to start thinking about heat wave events, I'm showing here a super flood event that occurred in 1983, when there was above average snowpack in the winter, but an anomalously warm period at the end of May and into early June that resulted in widespread melt that flooded streets of Salt Lake City, for example, so much so that they actually constructed these kind of artificial canals, if you will, to move water away. And during that same time, there was also so much melt in the Colorado River Basin that the Grand Canyon Dam faced the possibility of overtopping. And actually, plywood was apparently installed to help prevent this. So with this in mind, you probably have now kind of a flavor of the types of extreme events that we're looking at. And so what we've now defined and what we're calling is these heat waves are snow eater heat waves. And our definition of that is seasonally anomalous and above freezing temperature conditions that are sustained for several days, both in the day and the night, and result in impacts particularly on water resources and things like increasing flooding risk. So we've developed a workflow to identify atmospheric conditions that led to kind of similar 1983-like super flood events, such as those examples that I showed on previous slides, and also estimate the melt potential. And we're looking at, as well, current operational snowmelt models to really understand, are they able to represent melt during these types of events? And then we're also looking at and evaluating the spatial and temporal characteristics of these heat wave and melt events across a long historical record and generating essentially a catalog. And to do this, we're utilizing the 20th century reanalysis in order to identify heat wave conditions. The operational snowmelt model that we're looking at is the Snow 17 model, used to estimate melt potentials, both during snow eater heat wave days and non-snow eater heat wave days. And we're working on and we've developed essentially probabilistic parameter estimates to improve existing kind of operational models to better represent that enhanced melt that is seen and experienced on snow eater heat days. Okay, so we're utilizing a heat wave tracking method to follow these snow eater heat waves, and that's what you can see here. So that way we can isolate events that occur when the snowpack is present and also approaching that climatological peak and begin to melt out. So we identify temperature shifts that are anomalous and would be expected to result in essentially the ripening and rapid melt of the snowpack. So we're looking at a positive 6 Kelvin anomaly to the daily average 2 meter air temperature when that is above freezing. And so what's been playing here in the background is a loop through the 2 meter air temperature anomalies and the corresponding areas where snow is present and that anomaly exists. Okay, so I mentioned earlier that we're looking at operational melt potential models, and what I'm showing here is the change in SWE across time, and the blue curve represents that kind of out-of-the-box operational Snow 17 melt potential model for a period of time where we have a heat wave, and that's what's shaded there in gray. And what you'll notice is that this model does a good job representing the mean melt across the Western U.S. during this heat wave. However, its extreme, 90th percentile melt potential is much more constrained than the observations, in this case from SNOWTEL, actually indicate. So we've been developing melt potential models to add that enhanced melt, or account for that enhanced melt that the snow eater heat wave events result in. And so the figure on the top, the top panel there is what we just saw. And then I'm showing a couple other models that we've also now incorporated some additional parameters and in order to account for that increased or enhanced melt potential. And so what you'll actually see if you look at, say for instance, the second model here is now that we're better able to capture the extreme events with a bit of a degradation, though, still in the mean melt performance. But the hope here is that there's potential here to really benefit operational applications and think about preparing for these types of snow eater heat wave events. We've also used this framework to analyze long-term trends in heat waves, and I'll just summarize what we found here since the 1850s. Snow eater heat waves have increased in their aerial extent, decreased in their duration, increased in frequency, and also shifted when they occur to earlier in the season, when that first occurrence takes place in the year. Which again indicates that heat waves really that heat waves will likely continue to impact the way in which we think and really need to prepare for hazard mitigation areas, risk assessment, and managing our water supplies. And so these are really important processes worth investigating in snowy and mountainous regions. And for the sake of time, I'm not going to go into too much detail here, but I did want to mention that we're investigating synoptic weather patterns related to the events that were defined in the Snow Eater heat wave catalog and the slides that I showed previously. And these also use a 20th century reanalysis. And here on the left, you can see various characteristics and metrics associated with those events. And also a map on the bottom left where we're showing the mean 500 millibar heat anomalies over about almost 600 days, showing these types of heat wave events. And then on the right, I'm providing a few samples of cluster analyses that were performed using self-organizing maps with the aim of separating out distinct modes of atmospheric circulation for, again, those Snow Eater heat wave days. And what is very apparent in these examples that I'm showing are that there are variations in the ridge placement and the strength and the wave patterns that occur. So we're diving into these patterns and additional variables to better understand atmospheric patterns, atmospheric circulation patterns at various time scales associated with these events. I also want to just quickly mention and highlight that we have some very promising results from our use of a multi-objective optimization approach to link physically based recursive digital filter with a chemical mass balance to constrain, as a constraint, to estimate base flow and quick flow components and overall stream flow response, to understand the impacts of heat waves on these different components of the hydrologic cycle. And so we're examining the role of heat waves, both in terms of water quantity and water quality. And this is ongoing work to really understand recharge and stream flow rates in the presence of heat waves in snowy regions. And then lastly, I'd like to share this really nice snow drought dashboard tool that has come out of this NOAA project to visualize and explore the evolution of snow droughts and their deficits in terms of SWE across the Western U.S. at the HUC-6 scale. So I really urge you to take a look at this, play around with it, to monitor snow-till sites in your region of interest. And then just to wrap up here with some final thoughts, it's really critical that we develop a better understanding of the impact of heat waves and warming and their impact on the snowpack, especially as extreme events are expected to become more persistent and severe, so that we can really safeguard our water resources and mitigate those effects. So thank you for your time, and if you have any time for questions, please feel free to ask. So, thank you.
Thanks so much, Dr. Koenig, for a very interesting talk. A question, you showed the snow-till dashboard just a couple of slides ago.
Sure.
On snow drought. Can you just provide quickly the users of that? Do you have an idea of those people who tend to use this dashboard? And
yeah, so I mean that's freely available to anyone who's interested to go ahead and use it. I do think that there are potential for operational kind of monitoring of it. The thing that is really nice, I think, is not just that it shows the snow-till observations, but it also plots kind of that evolution of snow drought and looking at temperature and precipitation impacts, as well as the snow water equivalent, and kind of places that into different drought categories, similar to what you see with the USDM. So using those types of drought categories, which are essentially, probabilistic levels of how extreme the event is.
Thanks so much. Thanks again, Dr. Honey. And I'll pass it back to Lauren to close us down.
Thank you, David. Thank you to everyone in the audience and all of our speakers, Ping, Jane, and Lori, for your really great presentations. This webinar is being recorded and it will be posted on the NOAA Climate Program Office website within a few days. And again, as I mentioned at the beginning, registration is open for the second webinar of the series. So if you're interested, please scan the QR code on the screen and join us on March 19th to learn more about projects that have used modeling, monitoring, and analysis techniques to translate heat research into real-world applications and tools. Again, thank you to all the speakers and thanks to everyone for attending, and looking forward to seeing everyone next time.